Hey, Michael. Okay, so let's get this show on the road today. And we are going to be finishing up with normalization today. And in fact, finishing up with the logical design of a database. So after today, you should be able to look at a case study. And actually, we will do a case study, the hotel case study today. And you should be able to use a combination of entity relationship modeling and normalization to create a set of relations that model the problem you have. So we started normalization on Tuesday. We'll continue it now. I'm actually going to stop the video, just my video, so that I can get better throughput. Y'all can still see the screen, correct?
Yes.
Okay, perfect. Okay, so just a quick review of what we went through last time with normalization. So normalization, what we're trying to do is decompose a relation into groups of logically related attributes based on functional dependencies between the attributes. And normally, this applies when we either have two or more entities in a single relation, or where we have repeated instances of a descriptive attribute. So last time, the example we showed was here with branch address. We had it being repeated multiple times with a branch, and it led to an update anomaly, because when we update the branch address, we're going to have to update it in multiple places in the database, or else we'll have an inconsistency. And we also had two entities represented in this relation, and that led to insert and delete anomalies. So having redundant descriptive attributes leads to modification anomalies. Having two or more entities in the same relation leads to insert and delete anomalies. So insert anomalies occur because if we want to insert a new entity like branch, we can't do it because we would have to associate it with some staff number, because staff number is the primary key in this relation and it can't be null. So unless we have a staff member associated with the branch, we can't create a new branch. And similarly, if we delete all of the staff associated with a branch, for example, if we delete Mary Howe, we'll lose all the information associated with branch B7, because that's the last tuple associated with B7 in the branch. So we want to ensure that each entity is in its own relation so that we can eliminate insert and update anomalies. I'm sorry, insert and delete anomalies. And we want to ensure that descriptive attributes aren't repeated so that we can avoid modification anomalies. And the way we're going to do that is with functional dependencies. So we're going to identify functional dependencies among attributes. And that means we say that B is functionally dependent on A if each unique value of A is associated with exactly one value of B. And it's going to turn out that for the most part, each functional dependency is going to result in its own relation, with the left-hand side representing either a primary key or a foreign key, and the attributes on the right-hand side being the descriptive attributes. Okay, so there was a few requirements for functional dependencies. They had to be one-to-one, meaning that if for each unique value on the left-hand side, there's a unique value for that attribute on the right-hand side. It has to hold for all time, not just in the sample data and not with 99.99% probability. It has to hold regardless of what your data set is, no matter how improbable the data set might be. And finally, the determinant, which is the left-hand side, has to be the minimum number of necessary attributes. Okay, so we then talked about transitive dependencies, and you'll see how we use them in functional or in normalization. And finally, where we left off was with the process of normalization. So normalization is going to take us through a number of steps where the relations become progressively more restricted and less vulnerable to update anomalies. And there are, as you can see here, we start at first normal form, which is the least restrictive, going up to fifth normal form, which is the most restrictive. In this course, we're going to stop at third normal form because it's the most widely used. I'm going to give you a brief description of what Boyce-Codd normal form is, but it's pretty unusual. And in the homework assignments and tests, I'll only hold you responsible for third normal form. So normally, when you create your first relations, you'll be creating them from things like forms. And when you do that, you may end up with a relation that's in unnormalized form. So for example, I might take down some information for a branch and find that it has multiple phone numbers. And I list all of those in the same cell of the relation. So for example, I might have like, say, branch number and phone numbers. And I might have multiple phone numbers like 865-115211, 865-31, 865-400. And each of these is a cell. So we're not allowed to have this kind of table because there's multiple values or multiple values in a cell. So this is unnormalized form. Another example, I won't show it, but let's say I was taking a bunch of lease agreements and I was organizing them by property. Then I might end up with multiple lease agreements per property. And I might try to list all of them in the same cell. And that again would be an unnormalized form. So I want to be able to, the first thing I need to do is create a normalized table, which is first normal form, by ensuring that every cell, which is the intersection of a row and a column, contains one and only one value. Now in first normal form, it is permissible to have multiple entities in the same relation, like the staff branch directory relation that we've been using thus far. That's in first normal form. So to get to first normal form, we have to get rid of our multi-valued attributes. So basically, we're going to have to find a way to ensure that instead of having multiple values per cell, we have only one value per cell. And there's two ways to do it. One is if we know the maximum number of occurrences of an attribute, like if we know there's a maximum of 3 phone numbers, we can create one column for each phone number. So we could have phone number 1, phone number 2, and phone number 3. But the issue with that is it really makes queries verbose. If we want to see which branch has the phone number 865-444-4444, now we have to say, select the branch number where phone number 1 equals, or phone number 2 equals, or phone number 3 equals. And that gets to be fairly annoying. Also, we may end up having a lot of null values. If it's unusual to have the maximum number of phone numbers, we may end up with a lot of null values to represent phone numbers that don't exist. So this is not the preferred solution. The preferred solution is solution 2, which is we move the repeating data to a separate relation. You may remember that I said there's 3 types of relations: ones that represent entities, ones that represent relationships, and ones that represent multi-valued attributes. So when we go from unnormalized form to first normal form, what we're doing is creating relations that represent multi-valued attributes. So in this case, we'd create a relation for phone numbers, and it would have a foreign key, which is the branch number. And it would have, so you'd have phone number as the one descriptive attribute and branch number. And you might call it, for example, telephone. And now each tuple would be associated with exactly 1 phone number. So it would also be in normalized form. Okay, so this is the preferred way to deal with multi-valued attributes. And sometimes it's really the only practical way. So another possibility for a multi-valued attribute is dependent children. Sometimes companies keep track of dependent children for insurance purposes. There is no upper bound on the number of children you can have in a family. There's a TV show about a family here in East Tennessee that has something like 15 children. So in this case, without a even feasible upper bound on the number of the maximum number of occurrences of that attribute, you can't even resort to the create some number of columns for it. The only real solution is to move that repeating data into a separate relation. Okay, so we get to first normal form. It means we don't have multi-valued attributes anymore, but we could have 2 entities, 2 or more entities in the same relation. Now we want to move to second normal form. So what is second normal form?
Dr. Veazey?
Yep. Mm-hmm.
Sorry to interrupt. For first normal form, when you were saying creating the other table, I know that the primary key from the original table is the foreign key into the attribute table.
Mm-hmm.
You combine them up, and of course, then the names are associated. You know, the phone numbers are associated. You pair them together. Is that? Did you? I saw like if you could. How did you pair them up? Like, why the parentheses around them?
Oh, this is just my way of it's my way of showing a relation and the attributes in the relation. So.
Okay. I just want to make sure it wasn't like the new primary key or something.
No. So it would actually be, here's the telephone relation, and it has branch number and phone number. And it's like B003 865 111 5211, and then B003 865 3114281, and each one is in a separate row. Like that. So it was just, this was just meant to show, here's the name of the relation and its attributes.
Okay, thank you. I appreciate that.
You're welcome. Other questions? Always happy to have questions. Please don't hesitate to break in and ask a question. Okay. In that case, moving on to second normal form. So in second normal form, any non-primary key attribute, so say every descriptive attribute, well, that's not really true because you could have attributes that are part of a candidate key. So I really do have to be precise. Every non-primary key attribute is fully functionally dependent on the primary key. Remember, fully functionally dependent means that it is the minimum number of attributes required to determine a value. And if you can determine that value with one fewer attributes, it's not fully functionally dependent. So what we want to do to move from first normal form to second normal form is to remove any partial dependencies and move them to separate relations. So obviously, the first thing we have to do is identify the primary key because there may be candidate keys. And I will tell you that based on which of the candidate keys you choose, you may end up with a different set of second normal form relations. It's only when you get to third normal form that you end up with the same set of relations. And I'll illustrate that in a little bit. So now here's an example. Best way to do it is to show you an example. So here is our lease relationship. And so a lease has a client, a property, client name, property address, when the start of the lease is, when the end of the lease is, the amount of the rent, the owner number, and the owner name, okay? So in this lease, we're conflating actually three entities. We have a client, a property, and an owner, all in the same relation. But we're not, in this case, trying to yet separate entities. So we're going to choose as our primary key the client number and the property number. It turns out that those two attributes determine everything else. If you don't believe me, let's go through it. The client number is going to determine the client name. The property number is going to determine the property address and the rent, and the owner number. And then the owner number is going to determine the owner name. And then together, the client and the property is going to determine when the lease starts and finishes. And we're assuming that the client cannot rent a property multiple times. So that if we know the client and the property, we know when the rental period started and finishes. Now, here's what I mean by partial dependencies. The client number by itself determines the client name. So notice that client name depends on only part of this primary key. It doesn't depend on the property number. It only depends on the client number. And the same thing for the property address, the rent, and the owner number. They only depend on the property number. They don't depend on the client number. So these two dependencies are partial dependencies because each of the left-hand sides is a subset of the primary key. Then I've shown you the one transitive dependency here is owner number determines owner name. Notice property number determines owner number determines owner name. So that's a transitive dependency. And finally, there's a number of alternative candidate, there's a number of alternative candidate keys. So the client, since we're assuming the client can only lease one property at a time, we're assuming that the client and when the lease starts determines the property and when the lease finishes. And similarly, that knowing the client and when the lease finishes also gives us the property number and the rent when the lease begins. And then once we have the property number, we're able to determine the remaining attributes. So that's why the first two are candidate keys. Then if we know the property number and when the rent starts, we know the client and when the lease finishes. Now this also assumes that only one person is allowed to sign the lease. If multiple people are allowed to sign the lease, then this does not hold. But assuming only one person may sign the lease and they may have only one lease in effect at a time on a property, then, I'm sorry, that there may be only one lease on a property at a time, then the property and when that lease starts determines who's renting it and when the lease finishes. And similarly, knowing the property and when the lease finishes lets us know who's renting it and the start. And then again, once we have both the property number and the client number, we can determine all the attributes. So here's a full set of functional dependencies for this lease relation. And I would expect on an exam or a homework, you'd be able to find all of these relationships. Obviously, I would give you some information about it, such as at any given time, only one property, a property may be rented to only one individual at a time. I'd also have to tell you that in this case that a client would never rent a property more than once. Those would be required assumptions in order to get to this set of functional dependencies. Questions about this? Okay, so we now want to go from first normal form. This relation right now, this lease relation is in first normal form. We're going to convert it to second normal form by removing these partial dependencies. So we're going to, for each of these two functional dependencies, we're going to move the attributes in these functional dependencies to new relations. The right-hand side attributes are going to move out of the lease relation. The left-hand side attributes are going to remain in the original lease relation, and they're also going to move to the new relations, thus forming foreign keys. And remember, we have this lossless join property that we preserve, which is we can merge the decomposed relations and obtain the original relation. And by ensuring that the left-hand side attributes remain in the original relation, plus move to the new relation, we ensure the lossless join property. And then by moving all the attributes associated with a functional dependency to a new relation, we ensure that the dependency is preserved. That was the second thing we wanted to do with normalization, is preserve dependencies. Okay, so we're going to place each of these two functional dependencies into new relations, which we've done here. We call it the first one client, we call it the second one property owner. And notice with property owner, we also included any transitive dependencies. So while if you just looked at it, this was the set of attributes on the right-hand side. it is also the case that owner number determines owner name. So we also had to move the owner name into the property owner relationship. So any attributes that are part of a transitive dependency also need to move along into the new relation. And then you see we moved the right-hand attributes out of the lease relation. So client name, property address, rent, owner number, owner name, all moved out of the lease relation, which is now reduced to just these four attributes. Okay, and these two slides just reiterate what I was telling you, that we're moving the partial dependencies to new relations, and that attributes in transitive dependencies have to move as well. Okay, and then this slide is simply telling you what I told you before, that the left-hand side attributes remain in the original relation, but also move to the new relation, that this preserves the lossless join property, that all the attributes in a dependency move to the new relation, and that preserves the dependency in the new relation. Okay, so here we are now in second normal form. Okay, questions about second normal form? Okay, one thing that is important is that if the primary key is a single attribute, so if the primary key is a single attribute, then a relation in first normal form is also in second normal form. Can someone tell me why that has to be the case? If the primary key is a single attribute, why does that essentially guarantee that the relation is already in second normal form?
Because everything already depends on the primary key.
Very good. Everything already depends on the primary key, and because there's only one attribute, it's minimal. The only way I could get a partial dependency is if I have two or more attributes, and in that case, I could have some subset of the primary key determining some of those attributes. But if there's only one attribute in the primary key, there can be no subset of that primary key. Obviously, in the homework assignment and on an exam, I will never be so generous as to give you a primary key that is a single attribute. That will not be happening. So, but it is something that you should be aware of. Okay. Now, we still have not gotten every relation into what we call third normal form. So third normal form is one in which we don't have any transitive dependencies on the primary key. So here in the property owner, it is not yet in third normal form because there's this transitive dependency of owner name on owner number, and transitively, that depends on the property number. So we need to get rid of this transitive dependency. And it turns out that when we go from second normal form to third normal form, that when we reach third normal form, we have essentially ensured that every entity is in its own relation. So that's important because if you remember, when you have two or more entities in the same relation, then you can get insert and delete anomalies, and those are nasty business. So we want to ensure that we get to a restrictive enough normal form that all entities are guaranteed to be in their own relation. And essentially that is what third normal form gets us. Now, third normal form does not eliminate every possible modification anomaly, but it pretty much eliminates any possible insert or delete anomaly. At any rate, to get to third normal form, we identify our transitive dependencies and move them, the attributes in those dependencies, to their own new relation. And again, the left-hand side both stays in the original relation and moves to the new relation. The right-hand side attributes are removed from the original relation. So here, what happens is the owner number and owner name move to a new relation called owner. And the owner number, you can see, remains both in the original property for rent relation and has moved to the new owner relation. So now everything is in third normal form. So back here, client and lease were already in third normal form. And one thing that I should at this point out is with this lease relation, remember I had these alternate candidate keys. Notice that all 4 candidate keys involve the same 4 properties: client number, property number, rent start, and rent finish. And that the primary key also included those 4 attributes. So in fact, this primary key dependency and these alternate candidate keys, they are all still, those dependencies are all preserved in this final lease relation. So all of our original functional dependencies have been preserved. And by using those foreign keys, we can do a 4-way merge on client, lease, property owner, and owner. I'm sorry, 4-way join on client, property for rent, owner, and lease to get the original lease relation back.
Dr. VZ?
Yep.
Real quick, the alternative candidate keys that we had listed earlier, and yes, the method that you just talked about with functional dependency, you know, identifying the things that are fully dependent on the primary key, you know, composite or whatever. Is that a surefire? Like if we're asked to identify alternate candidate keys, if we keep it within, like, you know, we're trying to figure out what attributes to select, whatever, is that like a general thing? Like just look, you know, primary, identify primary key, identify full dependencies, and this just look at those attributes to identify alternate candidate keys?
That's a great question. I would tend to think that the answer is yes, but without thinking a bit more about it, trying to think back to the booking relation right now, and I think that the answer to your question is yes. I think that basically your primary keys and your candidate keys are probably going to, the dependencies are probably all going to involve the same dependencies, I think.
Okay.
But since that question's never been asked and I've never considered it, I'm not 100%. That answer comes with, say, a 80% certainty associated with it.
That's not too bad.
Okay.
Okay,
but
thanks.
That's a good, on the homework assignments, that would certainly be an excellent rule of thumb to apply.
Okay, great. Thank you.
You're welcome. Other questions? Okay, so basically, here's a summary of what we've been talking about with decomposition. So first of all, there's essentially 3 types of functional dependencies. There are partial dependencies that we use to convert first normal form to second normal form. So partial dependencies are dependencies where the left-hand side is a proper subset of the attributes in the primary key. The transitive dependencies are ones that we get to convert second to third normal form. And then we have our candidate key dependencies. And one of those dependencies will become the primary key. The remaining dependencies will not be used in our decomposition process. But as was just mentioned, most likely anything that is in a primary key dependency, well, certainly anything that's in a primary key dependency is going to end up being grouped with the primary key in the final relation, third normal form. And it is pretty certain that the candidate key attributes will also end up in that relation. Okay, that's where I was saying that's my 80% certainty. Now, what I want to do is go back for a moment and show you that you can get a different set of second normal form relations if you choose a different primary key. So let's say that instead of choosing the client number and property number to be the candidate key, let's say that we instead chose the client number and rent start to be the primary key. So the first thing that you should realize is, okay, and it determines the property number and the rent finish. So what is now our partial, looking now at these things, what are our partial dependencies? Someone tell me, if I choose client number and rent start to be my, I've lost my mouse. So I gotta get my mouse back. Uh-oh, my mouse is being, one second, my mouse is being held hostage. I can't see the cursor. Get my mouse back. There, I got my mouse back. Okay. Okay, can someone, if I say that client number and rent start is the primary key, what are now the partial dependencies? Anyone?
I would say whatever was, like the rent start is dependent on, oh God, I don't know. Never mind, I'm backing out.
Don't worry. So what we need is what we're looking for. Now we lost it again. So we're looking for a left-hand side that has a proper subset of client number and rent start. And there's only one such relation, and that is this one right here. So client number is a proper subset of client number and rent start. So it is our one partial dependency in this case. So what we would do is we would now only use this one partial dependency to get us to second normal form. So in second normal form, we would now only have two relations. One would be client number, client, and it would have client number and client name. But in second normal form, the lease relation would have all the remaining attributes still. So it would still have the client number, and it would still have the property number, and it would still have the property address, which I'll abbreviate as PADDR. It would still have the rent start. It would still have the rent finish. It would still have the rent, the owner number, and the owner name. Now, when we go from second normal form to third normal form, we would still have this as a transitive dependency, but now this one would also, this property number determines property address would also become a transitive dependency in this case. So in when we went from second normal form, so these would be the second normal form. When we went to third normal form is now when we would create the client with the same two values we had before. Now we would create a property for rent using this one. And it would have the property number, which I'm going, since I don't have a lot of space, I'm just going to abbreviate as P number, P address, rent, and owner number, which I'll abbreviate as O&O. And then I'd use this dependency to get the owner relation, owner number, and owner address. And finally, the lease now would be down to the client number, the property number, the rent start, and the rent finish. So in the end, we end up with the same normal form, third normal form relations, but the second normal form relation were different. So I just wanted to point that out, that the second normal form relations are dependent on which of the candidate keys becomes the primary key. The third normal form relations are not. They should be the same regardless of which candidate key you chose to be the primary key. Okay, and again, one thing Zoom doesn't do well is how it captures my mouse. Okay, so now what I want to talk about, we've talked about how we get from first normal form to third normal form. There is more general definitions of second and third normal form. We've been using a definition that relies on primary keys, but we could also use a definition that would rely on candidate keys. So we could say that a relation that is in first normal form, or that a second normal form is a first normal form relation where every non-primary key attribute is fully functionally dependent on any candidate key, rather than on just the primary key. And if we did that, then our second normal forms would all look alike. So I just showed you an example where, depending on which of the candidate keys I chose to be the primary key, I would get a different set of second normal form relations. If I apply this general definition of second normal form, where we eliminate any partial dependencies involving a candidate key, then our second normal form relations will always be the same. Okay, and then third normal form, the more general definition is that no non-primary key attribute is transitively dependent on any candidate key. So in practice, it is good enough to say primary key because, as you just saw, essentially when we got to third normal form, we already had everything removed that depended on either a candidate key or a primary key. When we got to this back here with this lease, the only attributes left in it were ones associated with the candidate and primary keys. So effectively, we had gotten it to this general third normal form. So it turns out that typically, if we've gotten something to third normal form using the primary key definition, we most likely have also gotten it to the general version of the third normal form. So in this course, we're not going to worry about the general version. We're only going to worry about the primary key version. So when you do your decompositions from first normal form to second normal form, you're picking partial dependencies only for the primary key.
Isn't this that Boyce-Codd normal form? This any candidate key stuff?
I don't think so. I actually wondered that myself, and I was doing some research on it, and it does not actually appear that generalized third normal form is the same as Boyce-Codd normal form. So let me show you an example, okay? And I think it may become more clear why that is the case. So,
okay, I just thought I heard that on Zybook when they were telling us about Boyce.
In the where?
The Zybook assignment we did on normalization.
The Zybook assignment was a little bit dodgy on it. That's why I went and looked. I thought the Zybook was dancing around it. And so when I went and looked, I came to the conclusion that actually Boyce-Codd normal form, I think if you look it up in Wikipedia, Wikipedia says that Boyce-Codd normal form is often referred to as 3.5 normal form, meaning 3.5 normal form, slightly stronger than third normal form and slightly weaker than fourth normal form. So my take on it is Boyce-Codd normal form is slightly stronger than even generalized third normal form. Okay?
Okay, gotcha.
Now, I will admit, I don't do research in the database area, so I would defer to someone who actually did the research in it. But my guess is there's a handful of such people in the world that are so mathematically sophisticated that they would be 100% certain of the distinction. I'm certainly not going to hold you to it in this class.
Appreciate it.
Okay. So as this slide says, we're going to stick with primary key normalization in this course. As I said, I think in something like almost 100% of the cases, by the time you get to third normal form, that primary key normalization and general normalization will result in the same set of relations. So I'm fine with primary key normalization. Now, the book does talk about Boyce-Codd normal form. So let's just spend a moment talking about it. I won't hold you responsible for it in either the quizzes, the homework, or the exam, but you should know what it is. So we say that a relation is in third normal form if any non-primary key attribute is fully functionally dependent on the primary key. But Boyce-Codd normal form, and you can actually see here, my definition of third normal form actually says depend exclusively on unique columns, which would be the generalized third normal form that I talked about, because the definition I'm using here is actually generalized third normal form. It says any non-key columns depend exclusively on unique columns. So Boyce-Codd normal form goes further, and it requires that key columns also depend exclusively on unique columns. So as far as I can determine, the only time that a relation in third normal form is not in Boyce-Codd normal form is if every attribute in that third normal form relation is part of a candidate key, and there is some dependency between those two attributes. So my take is that the only way that you can possibly not have third normal form relation be not in Boyce-Codd normal form is if every attribute in that relation is part of one of the candidate keys. So here's an example where a table is in third normal form, but is not in Boyce-Codd normal form. So it's giving employee information, their driver's license, state, the name, and the zip code where they reside. And so in this case, the employee ID is a candidate key. The driver's license number and the state is a primary key or candidate key, because a state never gives out a duplicate driver's license number. And then it turns out that driver's license number and postal code are also candidate keys, because the postal code, at least in the US, uniquely determines a state. And I realize that I've already contradicted myself, because name here is not in any of those relate or keys. So in fact, you can have a third normal form relation that contains a so-called descriptive attribute. So I'm going to have to modify the previous slide. At any rate, we have three candidate keys here, and we have one dependency among those candidate keys, which is that the postal code uniquely determines the state. So you'll notice that we have redundancies here in the postal code. Any place where two people live in the same postal code, there'll be a duplication of the state and postal code. So in that case, we can use this dependency of postal code determines state to further decompose the two relations. So we can move the postal code and state out of the original relation and into a new relation. And you'll notice this one, it's hard to say what exactly this relation is. It's not really an entity, because a postal code is not really an entity. It's not a multi-valued attribute, because every tuple in here is actually unique. You might say it's a relationship between a postal code and a state, except that postal code and state are attributes. They're not relations. So this kind of doesn't fit into any of the three types of relations that I have told you about. It is a fourth kind of relation, and I'm really not sure how to describe that type of relation. Just, it obviously exists. And the best I could probably come up with is that you might consider it is closest to an entity here. So a postal code kind of having an independent existence, describing a certain region, and it has things like state. It would have some geographical boundaries. So I think that probably if I were forced to characterize this, I would say that a postal code is probably an entity in this case. Okay, so this gives you an example of Boyce-Codd normal form. Again, I won't hold you to it, but it gives you an example where this relation right here is in third normal form, because certainly it's in third normal form. So the only non-key attribute here is name. And it is fully functionally dependent on each of the three candidate keys. So we are in fact in generalized third normal form. So I can now more definitively answer the previous question, which is Boyce-Codd normal form is in fact stronger than generalized third normal form. Looking at this relation is in generalized third normal form. The only non-key attribute is name. And it is, in fact, fully functionally dependent on each of the three candidate keys. So we are in generalized third normal form, but this relation is not in Boyce-Codd normal form. Okay, now, Boyce-Codd normal form is pretty unusual. Doesn't happen a lot. But you should know that in practice, many companies will probably go to Boyce-Codd normal form. That is as restrictive as they will get. It is generally considered fourth and fifth, and the higher normal forms are generally considered not to be worth it. Okay. So any questions about this? Again, I'm not going to hold you responsible for Boyce-Codd normal form, but you've now seen it. Okay. Now,
Dr. BZ, sorry, just so I understand, name, you said name was dependent on all candidate keys in this
yes. Table. The name here is dependent on each of the, here are the three candidate keys: employee ID, driver's license number and state, and driver's license number and postal code. Okay. So the, what was I? Sorry, lost my train of thought. So name is functionally dependent, fully functionally dependent on each of these three keys. Okay, if you can't remove, like here, so fully functionally dependent means you can't remove any attribute from this candidate key, and this name would still be unique. So if I remove the state and just have driver's license number, two different states could conceivably issue the same driver's license number to someone with the same name. So if I eliminate state and only have driver's license number, it is conceivable that I could have two employees with the same driver's license number and the same name. So in order for to uniquely determine Lisa Ellison, we need both the driver's license number and the state. Okay, and the same thing holds for driver's license number and postal code.
Okay, that makes sense. Thank you.
Okay, now I will tell you one other thing. So actually, what I want to do is go through the case study, and it is only going to take me about 15 minutes because I can do it fairly quickly. So let me go through a case study, and this is from an old exam. And it is a more expansive, you may kind of see it, essentially, we're going to end up with our set of hotel relations that we have been dealing with all semester long. But I want to show you how, if you were doing normalization, you might get to it. So when a person creates a reservation, you might actually have a form that looks something like this, where it has the hotel number, the guest number, the name of the hotel, where the hotel city is, the zip code, all this information about it, where the date, when the reservation begins, when it ends, what the room number is, the type of the room, the price. All of that might be included on the reservation form. And so your first pass at creating a relation might be one where you create a reservation relation that has all of these columns in it. So then I say you can make the following assumptions about this reservation. So a hotel number uniquely identifies a hotel's name and zip code. A zip code uniquely identifies a city for both hotels and guests, which isn't true in the real world, but we'll assume it's true in this world. So for example, my area code is 37920, and that covers both Knoxville and Seymour. But we'll pretend that it uniquely determines a city. A guest number uniquely determines a guest name and zip code. We'll assume that a room number and a hotel number uniquely determine the room type and price, which makes sense that you shouldn't be able to have a room at a hotel that has two different classifications, as for example, both a suite and two doubles. It should have a single room type and price. We're going to assume that a guest may not have overlapping reservations, meaning they can't double book. And we're going to assume that a room may not be double booked, i.e. have two guests trying to stay in it at the same time. So those are our assumptions, and they will allow us to figure out what our functional dependencies are. So the first question I ask is, give an example of an insert, an update, and a delete dependency. Well, there are three separate entities conflated in this reservation: a hotel, a guest, and a room. And essentially, in order to create a reservation, we need a guest. So if we want to insert a new hotel, but it doesn't yet, it's under construction, we can't do it unless it has a guest. But if there's no guest, we can't add it because the guest number can't be null. So in order to add a hotel, we need a guest, and that's an insert anomaly. The same holds for a room. Let's say we add a new room to a hotel, but it doesn't yet have any guests reserving it. Then there's no way to insert it into the database because the guest number can't be null. So those are two examples of insert anomalies. Then those are exactly the things that are delete anomalies. So for example, let's say that we only keep current and future reservations in this relation. And for some reason, some room doesn't have a current or future reservation. Then we lose the information about that room because there is no reservation for it in the system. So as soon as the last customer checks out of that room, we lose the information for that room. So that's a delete anomaly. And if for some reason we lose all reservations for the hotel, let's say we temporarily close the hotel for renovations. So on the last day that it's open, the last guest checks out, and now we lose the information for that hotel because for the foreseeable future it's closed and we're not accepting reservations. So there's no guest staying at the hotel. We lose all the information associated with the hotel. So that's the second delete anomaly. Then we also have some update anomalies. Let's say that we change the price of a room. That means we have to change it for every reservation in the system. If we forget to do so, we'll be charging different prices for the same room. Same thing if we change the type of the room. We change it from a king to 2 doubles. If we don't make that change for every instance of that room, for every reservation holding that room, then we'll have conflicting reservations where some reservations say that that room is a king and other reservations say that that room is a double. So that is conflicting or an update anomaly. Another possible update anomaly is if I change the guest number for Brad Vanderzanden, or I change Brad Vanderzanden's name. My name is misspelled a lot, so I call up and say, you got to correct the spelling of my name. Well, if there's multiple instances of, if I have multiple reservations, they're going to have to correct that name misspelling in every reservation, or else my name will still be misspelled on some of the reservations. So those are all examples of update anomalies. So in this case, any one example, I was only asking for one example of each. I gave you multiple examples of each. So then I'm asking, what are the functional dependencies for this relation? So let's actually go to the solutions. So the functional dependencies can be seen here. The hotel number determines the hotel name and the zip. So I get that directly from one of the assumptions. The guest number determines the guest name and the guest zip. I get that directly from another one of the assumptions. The room number and the hotel number determine the room type and the room price. I get that from a third of the assumptions. So if we go back, I said these two give me the, I'm sorry, not the, this one gives me my first functional dependency. This one gives me my second functional dependency. This one gives me my third functional dependency. Okay, let's actually just do it here. B, a zip code uniquely identifies a city. So up here, we actually have a hotel zip code and a guest zip code. Now I know that those are the same, so I'm just going to say that zip code determines city. Now, if you don't realize that you could also, if you want, say that guest zip code determines guest city and hotel zip determines hotel city, but that would actually be obfuscating slightly the situation because zip codes don't belong to a hotel or a city. They're actually independent of both. So it's really right to use B to get a zip code determines city. So then we want guests may not have overlapping reservations. So that tells us that if we have a guest number and a date from, that is going to uniquely determine the hotel number, the room number, and the date too. It also means that the date 2 can be used, and that also uniquely determines the hotel number, the room number, and date from rather. So a guest may not be a guest may not have overlapping reservations leads to both of these dependencies. Now you might be tempted to say, why doesn't the left-hand side actually be this? Guest number, date from, and date to, because they're not allowed to have overlapping reservations. So why don't I have to include both dates in the key? And the reason is it's not required because it's not minimal. If I know the date from, and I know that I'm not allowed to have overlapping reservations, that will determine the date too. So it's not necessary to have date to. That doesn't make it a minimal key. Remember, candidate keys must be, and full functional dependencies must be minimal. So if I included date to, it would not be minimal. I can get rid of it and still uniquely determine the hotel number, the room number, and in fact, date to. So that's why I didn't include both date from and date to in these left-hand sides. So then F, a room may not be doubly booked. From that, I can get that a room number and a hotel number and a date from is going to uniquely determine the guest and the date to, and similarly, the room number and the hotel number, I'm going to abbreviate now, and the date to uniquely determines the guest number and the date from. And again, I don't include both the date from and the date to because it would not be minimal. So both of these two come from F. And that gives us all of our functional dependencies. So questions about that, because I'm going to need to now move to the other page. Okay, I'm going to move to the other page. So this right here, what you see here, this just all gives me everything. And actually I did say hotel zip determines hotel city and guest zip determines guest city here. So I did temporarily make those separate functional dependencies. Okay, so the candidate keys for the relation are formed from the guest number and date from or date to, and alternative candidate keys are the hotel number, the room number, and the date. So these are the 4 sets, potential sets of candidate keys right here that you see. So I can choose any of these to be the primary key. And because it's the most compact, I choose guest number and date from. But on a homework, you could choose any of these to be your candidate keys. So if I choose guest number and date from, then you can go up here to try to find which dependencies of these 9 have either only guest number or date from as a left-hand side. So 2 has guest number as a determinant, And if you look through the rest of the list, there's no other dependency that only involves date from. So the only partial dependency is number 2. So to go from first to second normal form, I'm going to remove guest number determines guest name and guest zip from the relation and move it to a new relation. And you'll notice that when I do that, I create a guest info relation and I add the guest city. And the reason I do that is because there's this transitive dependency of that the zip code determines the city. So I moved the guest city also out of the booking relation and into the guest info. So this gives me my second normal form relations. Now I have to eliminate my transitive dependencies. So remember, there's 3 types of dependencies. There are your partial dependencies. You have your candidate key dependencies, which are 4, 5, 8, and 9. So the remaining ones are going to be transitive dependencies, which is 1 and 6 and 7 are your transitive dependencies. So we'll use those to go from second normal form to third normal form. Actually, I was missing one. The other one is here. The room number and hotel number determining a room type and room price. That is also a transitive dependency. So we're going to remove all of those into 4 separate relations. So each of these creates a new relation. And I collapsed these 2 at this point into a single zip code because it makes no sense to hold 2 different relations for the hotel zip and the guest zip, because in fact I would have redundant information. Zip codes are independent entities. They're not, or attributes. They're not dependent on a hotel or a guest. So I created 1 relation rather than 2 because I don't want to have duplicate information for zip codes. But you can see the room information is created from one of the transitive dependencies, the hotel info from another of the transitive dependencies, and then I removed the right-hand sides of all of those transitive dependencies from the booking relation. And so that's all I'm left with in the booking relation is the candidate keys. Okay. So someone asked me earlier though, is the only thing left in the original relation the attributes associated with the candidate keys? And I can now answer that. The answer is maybe, but not always, because when I showed you that Boyce Codd normal form, the employee name was still in that relation and it wasn't wasn't part of any candidate key. So you can't 100% say that anything that's left in the original relation is part of one of the candidate keys. That may not always be the case, but it's a good thing to start with. Okay, I think the final thing I want to say here is that I treated, you'll notice that I also had zip code here, and I used it when I went from second to third normal form. In that Boyce Codd example, the same dependency was actually there in some sense. It was that the zip code determined a state. And I might very well have used that transitive dependency when I was going from second to third normal form. And I can see that the reason that you don't use that dependency is that in the Boyce-Codd example, the postal code and the state were both part of candidate keys. And here, the zip code and the hotel city are not part of any candidate key. So that's kind of why here the zip code was moved when I went from second to third normal form. But in the Boyce-Codd normal form, the zip code did not move until I went from third normal form to Boyce-Codd. And the reason there was that the zip code was part of one of the candidate keys. And when you move a transitive dependency, you're only moving it if all of the attributes are not part of the primary key or part of the candidate key. So here, the zip code and the city were not part of any primary key, and therefore they got moved. Okay. So at any rate, that is our solution to the problem. I'm sorry, I know I went over by about 5 minutes, but wanted to finish so that you could get started on your next homework assignment. And we are now, as I said, finished with the logical design of a database. Next week, we're going to move into physical design, how we actually physically store relations in files in order to physically implement the database. So with that, I'm going to let you all go. If anyone has a question,